Okay, so let's go ahead and take a look at non-competitive inhibition. Key difference between non-competitive and competitive inhibition is the different binding sites. So the substrate binds to one site and then the inhibitor binds to another site. This inhibitor works independently of the substrate, so it can bind to the enzyme when it's free or to the ES complex. Because it works independently of the substrate concentration, you're always going to have the same percent of enzyme inhibited. Okay, so it's the same percent of enzyme inhibited regardless of your concentration for S. Okay, so if you inhibit 50% of the enzyme at low concentration, you inhibit 50% of the enzyme at high concentration. Because of this, and we'll show this on the graph, Km doesn't change. Okay, so the Km isn't going to change. Now, because you inhibit at a high concentration of S, okay, because you're inhibiting at a higher concentration of S, you can't have as high of a Vmax. What's going to happen is Vmax is going to go down, and we'll show this in the derivation with the Michaelis-Menten equation, how it's affected by non-competitive inhibitors. So we're still going to have this factor alpha. Alpha equals 1 plus I over Ki. We're going to say that the Ki is going to be the same for the enzyme regardless of whether or not it's bound to the substrate. Taking our original Michaelis-Menten equation, we need to multiply the Km and the S on the bottom both by alpha, factor out the alpha, and you end up with Vmax times concentration of X, and then on the bottom it's alpha Km plus the concentration of S. What you'll notice is that this Vmax over alpha term, this is now Vmax apparent. Okay, so the Vmax goes down. The Vmax apparent, or the Vmax observed, is equal to the true Vmax divided by alpha. Now let's take a look at some graphs. If uninhibited, we have this graph right here with a Vmax up there. What's going to happen is the inhibitor works independent of the substrate concentration. So it always inhibits the same proportion of enzyme. So what we're going to see right here is the difference between these curves is always a factor of, like, let's say 2. Okay, let's say that the inhibitor is always half the velocity. What's going to happen is because Vmax goes down, or because the inhibited velocity goes down at the same rate, you're going to notice that the Km is going to stay the same, because this line corresponds to either Vmax divided by 2 or Vmax apparent over 2. Okay, and that's the whole reason why you're never going to see a change in Km with the non-competitive inhibitors. Going to the Lineweaver-Burke plot, let's draw our straight line. Since Km doesn't change, all of these plots with the Lineweaver-Burke plots for non-competitive inhibition should have the same x-intercept. What's going to be different is the y-intercept, because y-intercept is 1 over Vmax. With the inhibitor, we're going to see that it has the same y-intercept, or same x-intercept, and the y-intercept is now 1 over Vmax apparent. Last thing to recognize, the slope gets steeper. Remember, for any Lineweaver-Burke plot, your slope is going to be Km divided by Vmax. In our case, we lowered the Vmax and kept the Km constant. Because of this, your lines are going to have a steeper slope, which is why we're going to see this line, or this red line, above the green line. Okay, inhibited is going to be above the no inhibitor. Different y-intercepts, same x-intercept.